Good morning, everyone. Today I will talk about quantum simulations with the Ultracold and Rydberg atoms, which are trapped in optical lattices. I think my research trajectory already has been given by Indranil. So what we are interested in mostly to study the physics of quantum phases and topological phases, which using these ultra-cold atoms and Rydberg atoms. So this ultra-cold atom physics I mostly did during my PhD time, and during my postdoc at Stuttgart, I was mostly interested in the Rydberg atom physics. And now at Hanover, we are exploring the phenomena, different physical phenomena which can happen in the if you take the mixtures of these quantum fluids. So as my talk goes on, you will understand what do I mean by all these big research areas which I am interested in. So from the title of my talk, I have written the word quantum simulation, and I think here I don't have to give too much of introduction. Everyone knows why we need quantum simulation. So idea is that if you take a particle which can be in two of the state, so in physics language it is speed of the particle which can be up and down. If you do a classical computation, then it's a bit, classical bit. So if you just want to describe the state of this single particle, you need two states. If you increase the number of particles, then the number of states grows. And if you have two particles, you require 4 states. And if you increase more number of particles, and if you have n number of particles, the number of states required to describe the system grows exponentially, and it is 2 to the power n. So from the classical supercomputers or classical computations, we know that there is an exponential growth of this memory. And if you want to do simulation, also there is a growth in exponential growth in time. And current classical limit is like you can simulate between 30 to 40 particles on these supercomputers. So if you want to study more or more number of particles, you need quantum computer, or you have to do quantum simulations, which relies on the idea that you simulate quantum system using quantum superposition. So in quantum simulation, you can represent this state for this n particle as a superposition of these all 2 to the power n states. And when you perform the measurement, you end up in one of these states. And this is how the idea of this quantum simulation works. So currently, there are 2 approaches to do this quantum simulation. So the main idea is that you make these quantum simulators in the lab, like in small systems, and you hope if you can study the physics there, then you know that the similar physics will be transferred in the nature which we see in everyday life. So the one approach is to make this analog quantum simulator, which relies on the idea of direct implementation of the Hamiltonian using these optical lattices. The another approach is to make digital quantum simulator, which is based on the qubit and quantum gate operations. So to understand it further, for an analog quantum simulation, you can understand it in this way, that if you want to see the time evolution of a state, which evolves under some Hamiltonian, so in this analog quantum simulation, you implement this Hamiltonian, which can be approximated to some simulated Hamiltonian, and this Hamiltonian can be directly implemented using these optical lattices. So this Hamiltonian will have atomic interactions, which you implement in these optical lattices via lasers. And then you prepare your initial state psi 0, and you let it evolve this state with some time, and this time is your simulation time is your real lab time. And then you see after time t that how the system evolves. You can also study another phenomena like ground state physics of this Hamiltonian and different phases or quantum phases of matter. So this Hamiltonian, this approach is non-universal. And what does it mean? That it is a Hamiltonian specific approach. Like if you want to study a different Hamiltonian, then you have to make a different setup for this. So, but it does not require too much of resources. And since it is a very strict, like it is a Hamiltonian based approach, you cannot correct more error in this approach. So yeah.
So what is this simulated Hamiltonian? So it looks like that you will probably be generating spin orbit coupling kind of thing. Right?
Yes, yes. So I think it will come, so you can implement different spin Hamiltonian, like quantumizing model kind of Hamiltonian, and you can also do spin orbit.
Right. So I was just curious because I don't know it.
Uh-huh.
So is there a class of Hamiltonian that you can simulate, or you can simulate all Hamiltonian?
I mean, especially nowadays people are interested in spin Hamiltonians. So it depends like how complicated your interactions you are taking and how complicated is your Hamiltonian.
But it looks like that will be only spin interaction, whatever spin interacts with. But in general, if I want to take a similar arbitrary Hermitian matrix, then what can you tell?
I don't know much about that, but if you currently know the interaction and how you can implement through laser, I think you can implement those Hamiltonian.
Yeah, so I think my question is like not a very good question. I'm just trying to understand that the quantum mechanics tells that I can have arbitrary Hermitian matrix as Hamiltonian.
Yeah.
And whatever I see in the lab, they come with particular interactions. For example, in optical lattice, you will have a spin orbit coupling.
Yes.
If you have two spins, you can couple with magnetic field.
Yes. Yes.
If you have light, you can have some polarization kind of, but not more than that.
Yes. Yes.
So,
But my point would be that with already what you mentioned, you can simulate a lot. So for instance, anything that you can do, you can just superconduct into it. Right? In say your quantum computer. You can do them in optical. Because
I'm not asking
You
how
want
much I can simulate.
a universal quantum computer in principle.
Asking about it theoretically.
Yeah, so that all of the Hamiltonian is now
Do we have some sort of result like that okay, you cannot simulate all this?
which kind of so highly non-local Hamiltonian would probably be very difficult to engineer in
No, I'm not asking difficult to engineer. I'm asking is it possible or not possible? Because so what I'm looking here is that if I have say interaction between spin and angular momentum, like orbital angular momentum, then can I simulate arbitrary Hamiltonian?
In principle, you can do if you can correctly implement, if you have correct lasers and all these systems you require. I mean, it will become in my career, in my career that I go, like when I will discuss this Rydberg atom physics, you will see like what kind of already Hamiltonian they have implemented and what kind of physics they are interested in.
And only one way to think about it is that you have your Hamiltonian of the system. So it's a parameterized system, right? So you have a parameter space that you can in principle tune from it's a minus integrate to infinity. So probably you would have to check and see whether this covers the space of all these.
Exactly, kind of the tunability of lasers that you have.
Yes.
But I think one way of thinking about it would be think of a Hamiltonian, which may not be which you may not be able to see. I mean, present a case, and then see whether there is a problem of tunability of it.
So it's not very clear.
No, because the thing in theory maybe you can, but then the practice practical
Actually, I'm asking only about theory. Whereas practice, a lot. Whereas optical lattices, for example, can simulate a lot of things.
Yes.
Interesting.
So, and the another approach is the digital quantum simulation, which relies on the so here, if you want to see the time evolution of this state, so here the idea realized that most of the Hamiltonian you can actually decompose in different Hamiltonian, like if you have interaction, you can decompose them. And then here you have to discretize the time, and all these decomposition of Hamiltonian act as a quantum gate, and you have to perform this discrete time evolution. So you switch on first like H1 interaction, then you switch it off, and then H2, and so it requires a lot of resources if you want to see the time evolution under this digital quantum simulation. But it is more universal approach. So here you can basically simulate any Hamiltonian, and also you can, since you have more control on these quantum gates, you can correct more errors. So here the idea is that you take all the atoms in a qubit in some initial state, and then you make this quantum circuit, which is based on quantum algorithms, and then you at the end you perform the measurement and you study the system.
So here also this question will validate that there is still like few bodies.
no, I think you can I can prove that you can simulate like in theory.
Yeah.
Any Hamiltonian operator can be written as in this form.
Yes.
The
non-local.
they may not be few body like you're saying. But in any Hamilton operator, you can write in that.
Yeah.
So in theory,
I might not even write it, right? If it is full body Hamiltonian.
you don't need to write it. But in principle, you can decompose any Hamilton operator. I can even specify a basis. So in this Pauli basis, because they're complete for
Yes.
that's what you can write it into. But of course, difficulty is whether you can actually engineer that.
Yeah, anyway, that is the question. So here is a theory which says that it's possible.
Yes.
But can you put arbitrary Hamiltonian here and then simulate using say,
It's an engineering question.
So, and nowadays actually people are also trying to combine these two simulations, like analog and quantum, so that if you can like overcome with all these errors and scalability issue and so on. So, but we are interested in the, but I am interested in more in the analog quantum simulation, or I would say atomic approach towards this analog quantum simulation. It has many advantages, like as we have already discussed that these optical lattices, now they can be created in the lab in much more efficient way in any dimension, and they are created by counter propagating laser beam. You can go in any dimension, and then nowadays they can also control the atomic positions of these atoms by using optical tweezers arrays, which is based on the idea that you create multiple of these dipole traps. So in optical lattice, it depends on the interference pattern. So you load the atoms in this, but in optical tweezers array, what do they do? That they take multiple laser beams and create many dipole traps, and then they start arranging those atoms.
And the typical size in laboratory of this optical lattices?
Sorry?
The typical size in laboratory of this optical lattice?
I think they can do like few hundreds of atoms. They can.
What is the size? Like 1 millimeter, 1 centimeter?
I mean, here it is in this tweezers array. They can arrange it in the distance of micrometer. And then they can also engineer interactions like short range interactions if the particles are like at a single lattice site, or if they are at a larger distance, they can also tune these interactions. So now, since they can implement all these lattice system in the lab, all these artificial quantum simulator, what are the things you can study with these systems? So the main thing which we are interested is that you can simulate solid state physics or electronic system using these optical lattice systems. So as we know that a crystal is a highly complex material, and it has impurity, disorder, and strong electron-electron interaction. So the idea is that if the system where interactions plays main role in this, where the quantum nature of the particles appear, can you simulate those type of systems in the lab first? Because these systems are very clean, tunable, and highly controllable. So if you can mimic the same physics there, and then you know that what will happen in a crystal. So some of the phenomena like a strongly correlated matter, where it shows quantum phase transition, then quantum magnetism, like implementing different spin models in these using these optical lattice. And on top of that, like many exotic phases, like topological phases of matter, if you can simulate them using these optical lattices or Rydberg atoms. So this, so what I am interested, it's like in this talk, I will mainly talk about topological phases of matter, such as quantum Hall state, and whether you can observe them using these neutral atoms or Rydberg atoms. And in the second part of my talk, I will discuss a few results about the mixtures physics, where you get what kind of quantum phases or like different phase separation phenomena can you observe in these mixtures. So let's start. So initially, phases of matter were described based on Landau's description, which states that at the phase transition, symmetry of a phase is broken. So you can understand it in this way, that a continuous rotational symmetry of a liquid is broken when it becomes solid, and the solid has a discrete translational symmetry. But not all phases of matter follow this paradigm. And later there were discovered the different phases of matter known as topological phases of matter, where this symmetry was not broken. So the famous example for this, to understand what a topological phase is, that you can understand it in this way, that a coffee mug is equivalent to a donut, as you can transform one into another without closing this hole. And this hole is a topological invariant here. And the known example of these topological phases of matter in the electronic system or condensed matter system is the observation of quantum Hall effect or quantum Hall state and topological insulators. So what is this quantum Hall state? So it was observed first in the experiment in a lab. So this relies you can understand it in this way, that if you take a 2D material, if you pass a current along x direction and a magnetic field along z direction, then there is a whole voltage generated along y direction. So then in this material, if you lower the temperature, the quantum nature of the particle becomes apparent, then this whole resistivity, which is equal to the this generated whole voltage divided by the passing current, this has a Plato as some filling factor, or here in this case integer filling fraction. And what does this mean is that this state is very robust. You see that you are increasing the magnetic field or changing the magnetic field, but this state is very robust. It is not changing. So it is independent of impurities, geometry, and microscopic details of the material. And it is also, this one, it is whole resistivity. Yes, whole resistivity. And here it is diagonal resistivity, because you will also have diagonal resistivity, which will be 0 at the same time, which tells that it is an incompressible state. So these states are very important, and they have been already observed in the condensed matter system. And then later there were also observed the fractional quantum Hall state, where this Plato occurs at the fractional filling. And this is more difficult to understand, because this integer quantum Hall state can be understood in terms of single particle physics, where if you take a charged particle in electromagnetic field, you end up with a Hamiltonian, where the energy levels are discretized, basically known as Landau levels. So how many Landau levels are filled? Based on that, you say that this is equal to 1/2 to 1 integer quantum Hall state or 2 integer quantum Hall state. But if there are interactions in the system, then this Plato can occur at fractional filling, and those are very difficult. So there is still no concrete theory which explains this fractional quantum Hall state.
What's the kind of interactions?
Electron interactions, basically. Yeah, strong. And also you require a high magnetic field to observe all those fractional quantum Hall states. So the idea. Yeah.
What is the phase here? Why do you say that as an example of the
I mean, a topological state. I mean, this is the different phase topological.
Because of the directionality of the field? What is the?
There is no phase.
There is no there is state.
I know, but it's not like that.
But this is a topological phases of matter. Of course, they say topological phases of matter.
No, phase directionally.
That's
in the direction. Yeah.
Yeah. I think, yeah, if you change the magnetic field, then the current, basically the carriers, which will be defined whether it is electron or
no distance in.
No.
Any distance
In the sense that they'll see, like, if with the change in magnetic field strength, you will enter this topological phase, you will stay there for some.
Okay, that
And
is.
Yeah, then you can say.
So you said like sphere like phase.
Mhm.
Can you say something like this?
Sphere.
Stair. No.
Sphere like phase.
No, what he says is that it's the directionality of the fields, and they go from one direction. I mean, if you change the direction from clockwise to anti-clockwise, then they're two different things.
Yes. So yes, they are very difficult to study in these electronic systems. So what people thought that, okay, if we can find these topological phases using these clean atoms, and by clean atoms, I mean these ultra-cold atoms, and we also refer in the literature as Bose-Einstein condensate. So what is this state, or what are these atoms and why they are so much clean? So you can understand it in this way, that at high temperature, the gas is classical, and there is these particles are kind of like a billiard ball. So there is interparticle distance between these particles. As you know,
When we go back, so we have,
Yes.
maybe it's important that we should understand what is phase. We have the y-axis is just resistivity.
Yeah.
Which, like Chitra said, that resistivity seems to be having a stair.
Mhm.
So do I think that one run of the stair adds one phase? Or is it wrong?
No, they are at a different filling. I mean, how many number of particles you have in a
So that is the quantization. Yeah, it's quantization of resistivity. So this means that different one will correspond to different kind of quantum state.
That states, but not that is not phase.
Okay, so what is the topological phase? There is topological phase on this side or no?
This is a topological state, and this is like,
So can I say that there are multiple topological states in this graph
Yes.
because there are
yes,
multiple?
because they depend on the filling. Like it is nu equal to 2 filling, it is nu equal to 3, 4, and this one is nu equal to 1 filling. So basically there is,
But that's the outcome, right? So I change magnetic field and my quantum state will be changing and y-axis is showing it through resistivity. Is that so?
Topological in the sense, stability, right?
yes, yeah.
No, no, it's not even clear now that if I can see these different runs as quantum state, is it true? That one resistivity corresponds to one class of quantum states or one quantum state?
Yes, because this is based on the number of electronic states you have in a lambda level. So basically you have to and you can understand it from the single particle physics, right? Like you take a charged particle in electromagnetic field.
So what we know that if I do this, what I was saying, I will have energy spectrum with
Yes.
the quantum.
Yes,
And that will be related to the resistivity.
that will be, that will tell you how many Landau levels are. So that will be related to, kind of, you can relate it like how many Landau levels are filled will decide all of your topological state. Like if there is one Landau level is filled, that means it is this state. If there are two Landau levels filled, that means this state. And the others are gapped.
So this is correct that different Plateau regions are different quantum states.
Yes.
And people are asking about phases. So what is the quantum phase here?
So can we
Or topological, sorry.
can we say what the Chern number is going to be or something? Like
Yes, you can calculate the Chern number for this nu equal to 1.
so they will all be different at this
Different, yes.
level, right?
Yes,
So that is a signature that there is some
Different.
Now we are looking beyond, so that number is not in the picture here.
That's a different thing like that. You calculate to verify whether it is really topological or
So
not.
I'm saying like, okay, the reason, the way you know that this is a.
No, we are not trying to, we are not able to
I
understand.
think they are stuck at the, they are stuck at the.
The existence of Chern number is actually the topological. Maybe
No, that was to detect the pairs. So if you see some particular Chern number or say multiple of Chern number or whatever the result is, so then you can say that there are different phases. But I want to define what is a phase here. So like it was said that is a running a phase, then we are not. So you can go ahead and we need to go about this thing.
Yeah, we can discuss later.
Not discuss, you have to tell because we don't know.
Yeah, okay. Yes. So yes, they were first observed actually purely in the experiment. So they were making this material, and there they saw that if you lower the temperature, then because in the classical Hall effect, what happens that you just get this linear resistivity. It is just directly proportional to the magnetic field. But this integer quantum Hall state appears due to because you are going to the lower temperature where quantum effects start to appear. So then people thought that let's see if we can obtain these topological phases or topological states using these ultra-cold atoms. So this BEC, the definition of BEC goes as like this, that if you have a classical gas at room temperature or high temperature, particles are basically billiard ball, and there is an interparticle distance between these two particles or these particles. As you lower the temperature, the quantum nature of the particle becomes apparent, and there is a thermal de Broglie wavelength corresponding to each of the particles. And if you further lower the temperature, this is directly proportional to the temperature or inversely proportional to the temperature. And as you further decrease the temperature at a critical temperature, these wave functions start to overlap, or these waves start to overlap with each other. And in theory, if you take T equal to 0 temperature, then this all macroscopic occupation, or in principle, all these wave functions becomes a giant matter wave. And this state is known as the Bose-Einstein condensate, and I refer them as ultracold atoms. So they are at such a low temperature that they are very clean system, and you can control them. You can control many of the interactions in the experiment, and you can also implement this high synthetic magnetic field, which is the requirement to observe this fractional quantum Hall state in this state by just using laser fields. And this is the first observation of BEC at MIT, where they have seen this peak at T is less TC, and your temperature becomes very, very much low. You see that all the particles occupy the single quantum state. So just to give an idea how much low temperature we are talking about. So here we are at the room temperature, and if you see the LHC physics happens around 10 to the power 11 to 9 Kelvin, and ultra cold physics happens here, order of nano Kelvin, and in the experiment actually they can up to go to the pico Kelvin actually. So there is an order of 10 to the power 21 of energy difference. We are talking about that much low temperature. So now let's start. What are the things, or what are the quantum simulations we want to do using these atoms? So as I have already mentioned, that these optical lattices can be created by counter-propagating laser beams, and these ultra-cold atoms can be loaded in the potential minima of this lattice. And the minimal model which describes these particles in this lattice is known as Bose-Hubbard model, where the first term is the kinetic energy term, which corresponds to the hopping of the particle from, which is the energy required to hop a particle from one lattice side to the another lattice side. The second term is the on-site interaction energy. So at a particular lattice side, there can be interaction between the particles, and mu is the chemical potential, which fixes the number of atoms.
So in laboratory, what is tuned in this happening?
Actually, they tune the ratio of J by U. Yeah, that is directly proportional to the lattice created, the intensity of the laser beams. So they can vary the depth of this potential, which will change this.
Remember,
You know, in that resistance, the particular limits of J by U.
Yes, sir.
so I remember that if J by U was less than 1 or greater than 1 to take you from insulator, not insulator.
Next slide. Yes. So depending on the competition, now since there are two of these energy scale, so now depending on the competition between this kinetic energy and interaction energy of the particle, like if the hopping of the particle is very, very less, that means if you make this potential to be sufficiently deep, that particle cannot hop from one lattice side to the another lattice side. They are localized at each of the lattice side, and this phase is known as the mode insulator phase. And if you turn on this hopping, where you allow particle from to hop from one lattice side to the another lattice side, then the system enters in the superfluid phase, and this phase transition, or this is the first quantum simulation experiment which they did in the lab in 2002 actually, in this paper of Greiners. So this has been
exactly solvable model for at least for long distance.
Yeah, so this is here I'm talking about this strongly interacting region. If you go to the weakly interacting region, you just get superfluid because this is DEC. If you just
Curiosity,
Yes.
so these both are exactly solvable models, or no? I think J by U going to infinity.
I think in the strong interacting limit, you will end up with a state which will be just that product of all these state at each of the lattice side. But for the superfluid, it will be entangled state, so you will have the superposition of different particles. So yes, you can solve it like in 1D. Actually, it is just the bosonic version of the Hubbard model, at which you can solve, right? This gives you this equation of this math equation, which gives you this law. So this is what I will talk about.
In the BEC case, is each of the node a BEC?
These particles are cooled atoms.
That is atom.
They are atoms.
This is not for BEC.
This is not for BC. So now we are talking about a strongly interacting region. So we are saying that now there is a strong interaction between the particles. So that's why you can arrange them.
So BEC, if I would like to visualize it, will be like on one energy level there are multiple particles.
Yes.
So there are many energy levels here. The first picture cannot be BEC. Second also.
Yeah.
I would like a ball of atoms somewhere in one energy.
At one place.
Yeah.
Yes.
Yeah.
That's what. Yeah. Yes. So first we study this model using our numerical method, that is single site cluster Gutzwiller mean field, and also we perform exact diagonalization method. So in single site Gutzwiller mean field method, what happens is that we take care of the hopping of the particle to the nearest site via mean field. And with cluster, we divide our whole system in forms of clusters. So here I have shown a 2 by 2 cluster. So within the cluster, we take hopping of the particle to be exact. And at the boundary, we take it via mean field. And we take the Gutzwiller ansatz, which is in which you can represent your state at a particular lattice site in terms of Fock basis. So, and depending on your how much number of particles you want, you can choose your basis. And for the cluster Gutzwiller, this state becomes more correlated because there are more number of particles or lattice sites in this one cluster. And then we construct our Hamiltonian, which I have shown, and we iteratively solve it and obtain the order parameter here, the superfluid order parameter, which will tell us whether it is the if it is 0, then it is incompressible phase, like multi-insulator phase. If it is non-zero, then it is superfluid phase.
Yes, so in this answer, so you have in your Hamilton PQ written, it's not nearest neighbor or second nearest neighbor, it's arbitrary, right?
So hopping is just the okay, 1 minute. Hopping is just nearest neighbor actually for me, and interaction is just on site. You can also take long range interactions, which will give you different physics. So it's just the nearest neighbor hopping I'm taking, not the long range hopping.
Why there two in this field? So what is
Because it is a 2D lattice, so PQ are two lattice site. Yeah, it's a bit. And at a particular lattice site, then you can write like there can be n number of particles, right? So this is what tells me. This is what this Fock state is telling me.
And this order parameter gives the expectation of non-condition operator.
No, it is the annihilation operator. It just tells whether a particle is created or annihilated at a particular lattice site.
But
So if there is a
order
particular number,
parameter doesn't seem measurable, right? Because it's the expectation of non-condition operator.
yes, but they do in the experiment. They measure the correlations, density correlations for. And also, like in the experiment, they also see the momentum state actually.
This is local order parameter.
This is local order parameter. Yes.
PQ is your site.
Yeah. Yeah. This is local order parameter. So,
But is it standard or people use other parameters as well? Order parameter for detecting the same kind of phase length?
I think here we just need like which tells you whether it is incompressible state or compressible state, which will just tell you based on the how many number of particles are fluctuating, right? For superfluid phase, there is a particle number fluctuation. So it should be some finite value. And for insulator, because it is insulating, particles are not moving, so it should be 0.
B is not relation first of all, so the spectrum doesn't seem to be bounded. So
But can we do something like this? So can I take, say, expectation value with respect to B plus B diagonal? And then I take another expectation value with respect to B minus B diagonal. And then do some.
B minus B is
So maybe I. That's a value
Yes.
somewhere.
Then you mean the current?
Yeah, like how do I, so this is like again, we are like stupid.
B plus B dagger is a good operator, I think,
Okay.
because it will be related to.
But this will be again the same because it's just the Hermitian conjugate of B. Like we calculate both. And they will be same, right? If there is not.
No, he is not trying to measure B and B dagger.
So I'm saying, how would you probably like see for us, like the question Uttam was asking is that look, B is not Hermitian, so it's not an observable.
Yes.
So how would one measure it? Like from a theoretical standpoint, like I cannot write this and say that, but in the lab, I'm sure there is a way to measure this. So we wanted to understand.
She said that density
Correlation. Yes.
You're not measuring it directly. You have to take the correlation.
Yes.
From there.
And correlation.
Yeah,
And
then the next question is, can I write some observable order parameter?
I mean, in theory, this is how people do, but in experiment.
No, because I know that like people talk about entanglement also, and they can compute entanglement using
Yes.
that order parameter.
Yes, this you can also calculate, but for this model, these two order parameters are sufficient.
And the correlation, what correlation you were saying that you measure the order parameter?
density correlation.
Density correlation. You can calculate the density correlation here.
There's
So you can
different sides.
how the
That-
correlation is.
Yeah.
Yes.
So that is not correlation still, right?
This is just the average density. This is
Yeah.
also again local order parameter. Because we know that
Yes,
for
sir.
the insulating case, it will be integer, the number of particles at each of the lattice side.
That is good.
And then for superfluid, it can be real.
And the correlation even means n hat P1 Q1 and n hat P2 Q2.
Yes. And you can fix a site and then calculate the correlation and see how does this behave. And this is what we do actually for this quantum Hall state, because there the density is real, and since it is incompressible phase, the order parameter becomes 0. But in the experiment, they cannot, as you said, they don't see this order parameter, but they see the correlation. So basically 2-point correlation. So there you can also calculate this D dagger B term actually. That is more observable. Yes, I think that's a good. So D dagger B term you can calculate.
And beta is n hat.
Yes.
Yeah.
Yes.
So
But no, at different sites.
A different hat.
from there, probably you can do some
D dagger I,
calculation.
D, J, this you can, they can see.
No, if I have different side, then it's not obvious.
No, if I have n hat I, n hat j, so,
You don't have n hat I and hat J.
sorry, n hat p, p1, q1.
No, I'm not arguing there. So you can compute density correlation, that is fine. And then you said that you can compute D dagger B. So I thought if it has the same side, then it's summation. But if you have B dagger B different sides, this is
2-point
still a-
correlation.
It's not.
No, it's not running. But this is like 2-point correlation.
There is also one correlation that I think.
So yes, so then using this method, so as I have described that if the larger is your cluster, because we are taking the correlation within the cluster exactly, it will give you better results. So we have seen that with a cluster size of 4/5, our results already approaches to the quantum Monte Carlo result. So this is the phase transition from mode insulator to the superfluid phase for n equal to 1 mode lobe I have shown here. And if you see that this mode insulator state is incompressible state, because you are changing the chemical potential, but the number of particles remains the same here. That is n equal to 1. And here they can fluctuate in superfluid phase. And this circle is the Monte Carlo simulation. And this, you see this green one is like kind of ours. Okay.
And good skill, I think, doesn't tell you what clock you will choose for writing the answer.
No, it,
4x time or 2x time thing, how do you choose them? By
I
drawing?
mean, you can just draw, like if you take, let's say 4/5 will be something like this, 4 on this direction and 5 on this direction. So 1, 2, 3, 4, 5, something like this.
How will I choose that? So whether I choose what you are saying or do something else?
You can choose any, so in our, in principle, in the code, you can choose any form of the cluster. It's just that the larger is the cluster, you are going to get more reliable results. So you see it here. And of course, it will grow the, sorry, 1 minute. It will appear here in your Gertz-Miller wave function. So
Yeah.
it will depend how big is your cluster size. So that many states you will have, and the Hilbert size will grow exponentially. So you cannot go much far because
I want to determine this cluster size, right, in some sense. So
Yeah.
I want some result so that I use optimal cluster size.
yeah, this is what we have done. Like we have checked that this is with the Monte Carlo we have,
So
because
this is
Monte Carlo,
numerical check, is that
this is
the-
numerical check.
You are comparing with Monte Carlo,
Monte Carlo.
and this that is Monte Carlo.
These circles are Monte Carlo.
Circles are Monte Carlo,
And then you see that if you just take single site,
yeah.
it kind of overestimate the superfluid region.
Mhm.
This is where you get the phase boundary. And then as we increase the cluster size, like 1/1, 2/2, 3/3, 4/4, we get this lobe to be, or the transition to be more closer to the exact one.
So larger view it seems exact, and the smaller view the cluster size matters.
Yes. And also like at the lower hopping, you get approximately good result, but the main problem happens at larger hopping, because now there are more number fluctuation in the system. And for that, you need more lattice sites to see. And yes, hopping is when hopping of the particle from one lattice site to another lattice site. Yes. So So
So what is the physical interpretation of that order parameter in the previous slide? I mean, just to understand why it is zero for not insulator and not zero for.
So what does this tells me? This order parameter is at a particular lattice height, or it is a local order parameter, which tells me whether I can create a particle or annihilate a particle. Like here in this case, if I can annihilate a particle. So if I can create or annihilate a particle, that means there is movement of particle in the system. So that means if it is finite, this order parameter, that means this phase is superfluid phase. If I cannot create a particle or annihilate a particle, that means atoms are stuck at some position and it is insulating phase. This is what it tells.
And then phi goes to zero.
Then phi goes to zero.
So zero to non-zero.
Yes.
That gives in
From order to disorder phase. You can understand it in the classical way also, like when you see this magnetization problem where you want to go to paramagnetic to ferromagnetic phase, you calculate this magnetization and which is zero and non-zero for a ordered phase and disordered phase.
So just thinking of this, I'm not sure if this is correct. So in quantum Hall effect, the phi is zero. Does that imply that vacuum is known also?
Yes, yes. So I will come in there. So yes, it will be plateau there. We will get yes. So yes. So this is what we have checked with our method, and now what we wanted to. So we know that quantum Monte Carlo gives approximately like good results. So but even with the if you consider a considerably large pressure, you can also get these results.
So you got chemical potential.
Yes.
And this all see the input parameters. So J by U and mu by U both are input parameters.
Yeah.
Then what is this plot showing?
This is showing a transition from a mode insulating phase to the superfluid phase. So what does the chemical potential does? It changes the number of atoms in a system, right? But in this law, your number of atoms are not changing. It changes.
the output is that super pi.
Yes.
So this is separating the boundary. I is zero there, I is not zero right. Yes.
Yes.
Oh.
Yes, yes. So this is a big
Exactly. So the line shows the separating point.
yeah.
I see.
So it is phi is zero here, or superfluid order parameter is zero in this law, and it is non-zero outside of it. Phase diagram. And yeah, so these kind of laws actually they have obtained even analytically for this 1D Hubbard model, and there it basically it goes like this, something like this. It's not parabola, but since we go the mean field predicts more better result in higher dimension, so that's why this is better here.
And then we'll leave like the degree of separation from this graph.
You mean first order or second order? Yes, so there are both actually. So this is the interesting thing here. So now you see that within this law there are integer number of particles. So if you fix, there is a phase transition where you go from 1 1 1 1 1 1 1 to 1, right? So the particles are just integer, but they are integer for mode insulator and for superfluid also. But you just identify them based on superfluid order parameter, which is zero here and non-zero here. This is the first order phase transition. But then there is another type of phase transition which comes from this line. Because here you go from 1 to, because here the average number of particles will not be 1. It will be
How
less than.
are you seeing the average number of particles?
So, okay, maybe I just draw this phase diagram. So this phase diagram which I am drawing here. So these phase diagrams somehow kind of follow these kind of contour lines actually.
Okay.
And these lines tell me, because this is chemical potential, and there will be one line here which will give me the expectation value of my number operator is 1, but this will not be 1. This will be like somewhere 0.9 or, and this will be like 1.1 or 1.2, something like that. So this kind of phase transition is the first order one, but this kind of phase transition is the second order one, because you are changing the number of particles also. Yeah. 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 So, but this is what we did, one of the check first, that whether our method works or not, because these are very complicated and Hilbert size grows exponentially. So it also takes some time to perform all these computations. So, but we were interested to study these topological phases, our main work. So the problem here is that these atoms which we are considering are charged neutrals. And if you put them in magnetic field, there is no Lorentz force. So you have to somehow implement this effect of this Lorentz force, or synthetically you have to implement this magnetic field in these atoms. And the idea relies on this concept of this Aronoff bomb phase. So like if a electron is in presence of magnetic field, if it goes around a circle, it acquires a phase. So the similar thing happens in the lattice system when particle hop from one lattice side to the another lattice side. And if it hop via this placket, it acquires this phase, which is a geometric phase. It is not the dynamical phase, it's just purely based on the geometry. And this is known as the pulse phase. So what does this phase do is that it, in this lattice system, this phase makes this hopping amplitude, which we were taking earlier, to be complex, and where this strength of this magnetic field can be given by this parameter alpha. So this implementation of the synthetic magnetic field, they can do it in the experiment by taking these two types of lasers. So here again they make this potential to be kind of superlative potential, like here it is higher and here it is lower. So when they hop from one lattice side to the another lattice side, the hopping is different than here and then here. So if when it goes through a placket, it has a phase. So the idea is that if you make this hopping to be complex and put it in your Bose-Hubbard model, can you get this topological phase or this quantum Hall state? And one thing here is to be noted that
is dependent for the right?
It can be Landau gates or symmetric gates, and
So the phi is also gets dependent,
yes,
like the one there.
I mean, yes. So if you take this, so here I'm taking just the Landau gates. So I just make my one of the hopping complex. If I take symmetric gates, then my both hopping become complex, but the physics will not change. So yes.
Someone has to justify, right? Because so you will declare your result in a particular case.
Yes.
This is like inducing some sort of, if you look at the Hamiltonian, inducing the symmetry breaking also, right? Going in one direction is not the same as going in another direction, right? Hopping in one direction is different because there's some symmetry breaking. Right?
Yes.
So the complex.
Yes. So that's why the quantum Monte Carlo will not work here, because it will suffer from the sign problem, and that's why we wanted to do it with mean field method and exact diagonalization method. And yes, we do then again we perform mean field method, cluster mean field method, and depending. So here I have shown two of the results for synthetic magnetic field alpha equal to 1/5 and 1/2, and we do get these incompressible state at different filling factor. And these states are the quantum Hall state, and they are incompressible. You can see that as we are increasing the chemical potential, the state is not changing. And also we have done another check, like we also calculate the 2-point correlation function, which decays exponentially in the bulk. And also we have calculated Chern number for this nu equal to half state. So yes, you can get these states in optical lattices, but until now they have not gotten it. So they are still trying. If they can observe this state in this clean system, then you can understand better these fractional quantum Hall physics. So then in the next project at Stuttgart, we wanted to study Rydberg atom physics and whether you can simulate these topological phases using this Rydberg atom. So a quick recap: a Rydberg atom, it is a highly excited atom. That means a electron is excited to this higher principal quantum number state, and these states are known as Rydberg state. And atom interacts in these Rydberg states, or all the interactions happens in this Rydberg state. And since electron is very much far away from the nucleus, these Rydberg atoms have some exaggerated properties. That means they are very huge. They have a long lifetime. That means you have enough time to perform experiments, and they have van der Waals interaction. And on top of that, because they will have this spin orbit coupling here, which gives rise to the dipolar exchange interactions, which naturally gives rise to this pulse phase, which we were implementing in optical lattice wire lasers. Here it directly comes through the spin orbit coupling.
So how
So
do
what
you
they-
decide that when you need the Rydberg limit, because this looks arbitrary.
What?
So for example, n equal to say 6, 7,
No,
you
it's, I think in the experiment, they typically take n equal to 60.
n equal to how do they decide that? What is the property? Like the deciding criteria that if this satisfied by the atom, then I will call it Rydberg.
I mean, any atom can be Rydberg atom. It's not the atom which is
That is why I am
called
looking for a criteria, so that
periodic table. But idea is that the further you take the atoms, like you have this long lifetime to perform the experiment. So also,
I mean, if I go very far away from the nucleus, I might die as well, right?
yes.
You typically take very large
Yes.
samples, like
Yes.
medium, senior, those sort of.
Yes.
So that you get more far
So the
away.
nucleus will be bigger there as well, right?
Sure, but you have many orbitals and you go to these high angular momentum.
And then I might get out of the orbit if I go too far away, right? So I want to know how do I decide that?
And why I did not understand is why the lifetime will increase if you go to very high intensity. Intuitively, it seems the other way around, right? And if you are at a very high value,
Exactly, I might get out of the orbit.
yeah, you may, I mean, what, firstly, it's almost continuum state. So n can change very easily. That is one thing. Secondly, any kind of interaction would like to stabilize the system, bring it down to a lower end. So it's counterintuitive that it has high long, I mean,
I mean, long lifetime to decay to come back to the ground state. This is what I mean, sir. If you
but
go
why? I mean, intuitively, it seems that once you have taken let's say an electron very far away, the high quantum number, it would like to come back.
Right? I think
Why would it have a higher lifetime? Not very intuitive. There must be something.
unless there is some meta stable or some other properties there, so that it's stable as it is.
I mean, long lifetime, I mean, I think what they mean is in terms of performing the experiment. Like the the kind of interaction
It's long
long
enough
enough for them
Yeah.
to perform. Like their interactions are ordered in of like megahertz, and in with respect to that, they say that this is enough to perform the experiment. It's not in the usual way we think. Yes. Okay, so what they have already done with this using these Rydberg atoms is that they have already implemented this quantum Ising like model, where they have considered these Rydberg atoms as a two-level system, and where these two-level systems are coupled by this Rabi frequency, and there is a detuning of this state with delta parameters, which naturally gives rise to this quantumizing like model, where the first term comes from this longitudinal magnetic field or Rabi coupling term, the second term or the sigma x term, the second term comes from the detuning, and this third term is the Ising interaction term. So like the particles are interacting at site I and j, and which comes via the von der Waals interactions. And this Hamiltonian they have already implemented in the lab, and they have seen this transition from paramagnet to antiferromagnet.
Sorry, can I ask like what is GI and RI? These are like
GI and
for the Rydberg atom, like in that figure.
which one? Bigger.
Yeah, this two-level picture that you have.
Yes, yes.
Yeah. So GI and RI are what? Like these high angular states?
Yes, these are in high angular number. So this is the ground state for, let's say, for n equal to 60 s half, this here, and this is in the p manifold, and then rest of the state you just isolate.
You're in a superposition of these two.
These two levels.
You can tune them.
Yes, you can tune this Rabi coupling and this detuning, and based on that, you can draw this phase diagram from paramagnetic to
And you
antiferromagnetic.
get a power law decay kind of between interaction.
Yes, this is just the von der Waals interactions. This is von der Waals, it goes at r to the power 6. And also they have seen this symmetry protected topological phase, like using this SSS chain by just considering these two-level atoms in this system. And this has also been reported in like in our group also they have contributed in this paper. This was the first signature that they can actually see these symmetry protected topological phases using these Rydberg atoms. So what we were interested here were that not with the 2-level system, but with the 3-level system. So where you have, like in one of our this project, where in the experiment what they have implemented is that if you consider this Rydberg atom in a 3 atoms or 3 in a triangular geometry, or just by taking these 3 atoms, and at each of the atom there is a 3-level structure, and in the p manifold or in the excited state you have 2 of the excitation, and now these excitations are kind of like your particles, they can hop within the lattice. And
the 3 things is the number of levels or is number of particles?
number of energy states, like they can couple these energy states via Rabi coupling.
So you have basically like Euclid kind of thing.
Mhm.
And
What
I mean, word is not important. So you have 3 levels, right?
3-level system. And like the ground
And
state,
is 1, 2, 3. You said that these are 3 atoms. So
there are just 3 particles or 3 atoms. Particles are atoms, like you just arrange them in a triangular geometry.
so these are 3 atoms, and each atom has 3 levels.
3 levels, yes.
Okay.
And in these 3 levels, like there are 2 types of excitations which they have considered, like plus excitation and minus excitation from p manifold, which actually can hop. So at each of the lattice side, there is either a plus excitation or minus excitation, or there is no particle, or they are in the ground state. And so this kind of 3-level structure actually gives rise to the 2 types of hopping or 2 types of processes. Like one is the resonant process, where a plus excitation becomes plus excitation, a minus excitation becomes, when it hops, becomes minus excitation, and then there is an exchange term where a plus excitation becomes minus excitation. And how does it do it? That like it's a second order virtual hopping process where a minus excitation first becomes plus excitation, and then again it becomes minus excitation, and this terms comes via the second order virtual hopping process. And since this is a off-resonant process, to conserve the total angular momentum, this acquires a complex phase. And this phase has been demonstrated using these 3 atoms in this one of the experiment with Antoine, where I was also in this paper. And there they have shown that the particle moves actually in a chiral way. This is the demonstration of this complex phase, or this phase which is coming from this spin-orbit coupling. So in our main project or next project, what we wanted to do is that to consider this 3-level structure and use this dipolar exchange hopping, which gives directly the pulse phase in a honeycomb lattice geometry, where at each of the lattice site we consider again this 3-level structure, and you apply like electric and magnetic field to isolate the Rydberg state, and the atoms only interact in this Rydberg state. And then what you can do is that now these 2 excitations are kind of like your 2 particles, and the interactions comes from this dipole-dipole interaction, or the Hamiltonian, mainly the Hamiltonian comes from this dipole-dipole interaction, where this first term is your usual dipole-dipole interaction, the second term comes from this exchange interaction, and the third is from spin-orbit coupling. So it's the same thing that, so the main idea is that you can actually have this spin flip-flop kind of hopping in these particles. And since we are interested in more in these topological phases, so you can translate this Hamiltonian into this particle system. So where we say that these plus and minus excitations are my 2 particles, which have this creation and annihilation operator of A and B. So it will have direct hopping of these excitations, plus and minus 1. And this will also have this exchange hopping, which will have a pulse phase in the hopping, which naturally comes here via this spin orbit coupling. And also intuitively, you can, what do I mean by these 2 processes like this?
So these are not the Bosonic kind of operator, the
Yes.
AIS and BIS. They have finite length.
Yeah, effectively you are simulating.
Simulating. There's a simulation there.
And what is the size of the honeycomb lattice that you can simulate?
Okay, I will just come next. Next is that one. So basically the process is that, like the direct process is that you have site I, site J. So plus excitation becomes like goes this ground state goes to the ground state. Again, it becomes the plus excitation. But with this off resonant process, it goes from plus to minus. And you can actually map it to these hardcore boson problems, or like consider them as a bosonic particle and write this Hamiltonian. And now we have long range hopping also, and this pulse phase in our system. And now system becomes more complex because we have 2 particles. So the Hilbert size will grow, of course. So we do, so the in my previous postdoc group, there was this one PhD student, okay, now he's postdoc, and he has written this pair interaction software. So where he has written this software where you just put all these parameters like this principal quantum number and all these things, and it automatically calculates the Rydberg interactions. And from there, we found that if you take all these parameters, you should get a fractional churn insulator state in this system.
So,
And this is, yes.
sorry, so I know that the algebra is different. So AI here, they don't follow bosonic algebra because one will like annihilate say NF particle because there is nothing n plus one, right? So they don't have similar algebra. So mathematically they are not equivalent. And what do you exactly mean by that? You simulate this through bosonic operator?
So they are hardcore boson operator. That means either there is a particle or there is not a particle.
Yeah, but so it's not boson.
Yeah. No, no. Also, there are not. Also, we have a constraint that at a particular site, either there is plus excitation or minus excitation. There are never both excitations together. So that's why you can reduce the Hilbert size a bit because you are reducing all these states where these both plus and minus excitations are there. So we vary now your question, how much long we can go. So we take different oscillations of these honeycomb lattice starting from lattice size to 16 to 28. And if you see that at 28 lattice size, the Hilbert space is already order of million size. And here we have done the exact diagonalization, and here we have shown that for this fractional, so this idea comes from the condensed matter, like if you have energy bands and if you fill them like a half filling, if they are completely flat or if they are topological, they should show these topological properties. So this is what we are doing here with exact diagonalization. We are fixing the filling at half filling, and then we are calculating these energies. So we have shown that at that the ground state is doubly degenerate and it is gapped from all other excited states. And it has so, and then since it is a topological state, we also calculate Chern number. And so first thing is to check is that since it is a topological state, if we give a little perturbation, and the perturbation here we are giving in terms of the twist along x and y direction, and the gap should not close between ground state to excited state, and this is what we are seeing. And if you just do it for the full space of these angles, we see that there is a homogeneous Berry curvature and the many-body Chern number to be one we have found. So what we have given here, the proposal that if you take all these parameters in the experiment and you can design this experiment, you should see this fractional Chern insulator state. Okay, so now I come to the, I think I have some time probably.
Yes, you have 27 minutes.
Okay, then I will not take much. So now in the second part, what we are interested is quantum phases and phase separation in the mixtures. And the mixtures here are different. So like in the classical fluid, but we see that whether two mixtures or two fluids mixes with each other or not, it depends on the interaction between the particles. But in the classical fluid, it is the van der Waals interaction which decides, right, whether they will mix or not, or whether they will phase separate. So the question here is that what happens in these quantum fluids, which I was talking about, like DEC or this condensate. So here also you can drive this transition from the miscible phase where they mix with each other to the immiscible phase where they do not mix by varying this interspecies interaction between the particles. So this is the criteria which follows there in this continuum system of Bose-Einstein condensate. And this is the on-site in terms of on-site interaction, they have seen it in the experiment. This is one of the experimental figure I am showing where they have shown that this they have taken two of the isotope of rubidium atom where in the lower panel they mix, and here there is a side-by-side phase separation. Now the question is that this is for the on-site interaction or the short-range interaction. What will happen if you take the long-range interaction and you go towards this lattice physics, like the strongly interacting limit of the particles? So these long-range interaction also they can implement in the experiment, but you have to choose a different atom, like highly magnetic lanthanide atoms, which have dipolar interaction, because the dipolar interaction will give you the interaction at the long range. And so in this project, what we wanted to study is that whether you can drive this transition from miscible to immiscible phase by just varying these long range interactions of the particle. And also we have taken, so the system that we are considering is now mixtures. There are these two particles are like two different species. So there is a hopping of the particle from one lattice side to the other lattice side. Then there is an interaction between the particle and on-site interaction between the particle and within the particle. And also there is long range interaction. Here we are taking density interaction, just the nearest neighbor. And there is also, because of these dipolar atoms, the other types of hopping can also arise here. So, and that hopping is like particle will hop from one lattice side to the another lattice side only if there is another particle present. So this is known as the density dependent hopping. So it will only hop if there is another particle there. So in this project, what we have shown that you can drive this phase transition from immiscible to immiscible phase. We have scaled everything in terms of on-site interaction, and you can purely derive it based on this density-dependent hopping or density-density interaction or long-range interaction in the experiment. And this you can do in strongly interacting regime, which will be like they're trying to do, but it's also a bit difficult here to do, but I think they are trying to do in the experiment. On top of that, since we have this different hopping, like density-dependent hopping, which is different than the usual hopping of the particle, and we take it of the opposite side, we end up in a different phase known as the staggered phase. And in the staggered phase, so in the usual superfluid phase, what happens that your density is real, average density is real, and the superfluid order parameter is also real. But in the staggered phase, this superfluid order parameter has a staggering in the parameter. So, and here what we have shown is that in this staggered phase, this criteria is reversed. And the theory comes from the idea that for the superfluid phase, the minima of the energy lies at k equal to 0 momentum, but for staggered phase, it lies at k equal to pi. And that's why it is reversed. And also staggering in superfluid phase. Another thing what we are interested in this mixture is here at Hanover with Lewis is that the idea is that if you make this system more complex and you want to study multi-layer physics, like because why people want to study this multi-layer physics, because they want to go towards this graphene type of physics. And this also you can do using these atoms, because there is tunability. Nothing is stopping you to do any theory. So here the idea is that you take these atoms in two of the layer and you arrange in, so in one layer there is one type of atom, another layer there is another type of atom like blue and orange, and you arrange in such a way that they form kind of a checkerboard pattern. So, and also you can adjust the height between the layer. So here what we wanted to see is that now they can interact. So, and the interaction is actually long range, like everyone interacts with everyone. So this atom can even interact there. So like all interactions we are taking. And this becomes a bit complicated to do in numerical simulations because there will be many metastable states present in the system, because we are considering the long range interaction. So here the idea was that if you take the half filling of each of the atom, can you get different kind of crystalline phases? So if you just have only nearest neighbor interaction or single particle in the lattice, you just end up with this checkerboard kind of pattern in the system. But here what we are observing that just by varying the height of these two layers, which directly correspond to changing the interaction between the particle, we end up in the different types of crystalline phases. And since as we go to the lower and lower H, there we are increasing the interparticle interaction between the atoms. So that means system is going towards phase separated region. And this is what we are seeing here. And we have seen here that the effect of the hopping, because this is just the classical energy calculation which you can check, because this is about arranging the atoms at different position, and you know the interaction, dipolar interactions, and you can, here we are seeing that there is actually this three type of states should occur at j equal to 0 when there is no hopping of the particle. But if you take the hopping of the particle, does all these crystalline phases survive? And yes, they do survive, and this hopping is they follow this kind of like super exchange process. I don't know how can I explain it. So like if you just see, if you know the Hubbard model, like this idea of super exchange actually comes from this Hubbard model, like because fermions they cannot be, like two of the fermions cannot be at the same place. So if they hop, they can increase, like there is no hopping there, direct hopping, because otherwise it will not follow this Pauli exclusion principle. But the hopping can also occur there via super exchange process. So like first particle goes, like if you just take the two of the atoms, so particle goes at this side, other side, and then it comes back. And in that way it can happen. And this process is known as the super exchange process. So this is what we are seeing here, and this is what.
Color.
Sorry, which color? No, these are just number. Here, yes, here it is order parameter. This is here we are calculating density interaction.
It's just the two there.
Yes, yes.
Just two there, you are tuning
The height. So tuning the height means changing the interactions between the particle, because if they go like this. Okay, and the last slide is that we have also done some work with the generation of this magnetic flux in this Rydberg atom, where we have again used this spin orbit coupling, and here we have shown the idea is that if you want to generate a homogeneous magnetic flux in these blue atoms, you take these red atoms as the background atoms or angela atoms, and the hopping comes via these angela atoms, which is complex. And this we have shown that if you just track this hopping of this single particle, and you can generate this homogeneous flux using this geometry. This is the proposal which we have given. They can do it in the experiment. So here the advantage is that compared to the optical lattice, that in the optical lattice they can generate it. There is a generation of staggered flux, but here it is more homogeneous. And this is something different, not related to ultracold atom, but related to topology, which we have done with Chitta here. And here the idea is that it's similar to this SSS chain model. If you know, if you just see this lower panel of these atoms, it's these three atoms you can consider as a rock, paper, scissors cycle. Like they have three different mass rate. Like if mass is transferred to mass transfer rate from this side to this side, and this side to this side, and this side to this side is different. So if you just arrange this atom in this geometry, and here our idea was that we wanted to go towards the 2D system, but we just took this 3-layer, and you can tune this rate of the mass transfer. And by just tuning this rate, which I say here R, if you take it R is less than 1, you go from a trivial phase to the non-trivial phase if you take it R is greater than 1. And at R equal to 1, the gap is closed. So there is a topological phase transition. As you go from this state to this state, you have to close this gap. And this is what we have shown in one of the paper. And in Chitto and their group, they have done this non-linear dynamics, which is bit different than the linear system, because now they are seeing this transition in this non-linear system, and where we have seen that if you take R is less than 1, the mass is transferred via edges on this side, and here it is switched. And just by switching this rate of this mass transfer between these two atoms. Okay, so at the end, these cold atom platforms are very nice, very interesting, very controllable. So you can study many of the things, like you can go from isotropic to anisotropic interaction, and you can study dipolar gases. You can go from atomic to condensed matter physics, and you can study many body physics, or this is strongly correlated matter. You can go from ground to highly excited state, and you can study cold plasma and Rydberg gases. You can also go from physics to chemistry and study ultracold molecules. By the way, they have already achieved now BEC with molecules. So this will be even better than the Rydberg atom physics, because there you have to control so many things. But if you have molecules, I think it will make your life easy. And then you can also go from fundamental to application and do quantum computations with these atoms by considering this state as a qubit state. And at the end, I want to thank my group members from Hanover, Louis, and other members in the group, and in Stuttgart, Hans-Peter, and other people, and in PRL, my supervisor, Dilip Engam, and our experimental group at Paris, Antoine, Professor Antoine and Thierry Lahai. And thank you. If you have any questions, I'm happy to take it.